Yashwant sir, are you there? हाँ स्टार्ट कर दिया सर आपने कनेक्ट कीजिए। वरुण एक चीज बता तेरे भाई का टूर्स एंड ट्रेवल्स का काम है ना। तो अगर जैसे अपने जयपुर में एक दिन के लिए थोड़ा घूमने के लिए अगर फ्यू कर दो तो जैसे नॉर्मली 4 आवर्स का तो 4 आवर्स का 8 आवर्स का चार्ज रहता होगा। पार्किंग वगैरह सब बनाएंगे तो चार्जेस जरूरत है जयपुर लोकल। हाँ 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 हाँ, इधर भी घूमना है। और इनिशियली तो जैसे बापू बाजार हो गया, वहाँ कुछ शॉपिंग वगैरह करना है। सही है। चलो एक बार ठीक है ठीक है। कुछ कंसेशन देंगे कि नहीं फुल नाम से? चलो चलो।
Hello, audible?
यस यू आर ऑडिबल। ठीक ठीक ठीक। ओके। वेट अ सर। चलो। वरुण है। चलो बस चलो उसके भाई का उसके जयपुर में। जयपुर में।
Hello, sir, is my screen visible?
विजिबल सर विजिबल।
So, sir, shall I start?
यस सर।
Hello.
You can start, sir. You can start. Participant,
Okay,
we are
okay,
going to start the session. The session is taken over by Dr. Yashwant Puri, sir. So go ahead, sir.
okay. Mm. Yeah, good afternoon, all. So we have already discussed about the integration. One second. Yeah, we have already discussed about the integration of smart manufacturing in AM. Like we have already discussed these 7 parts. So first part we have already taken real-time sensors, defect detects, process monitoring and control you have already discussed, and the CCD spectrometer and NIR spectrometer we have already discussed. The optical sensors, then acoustic sensor also have discussed. So this is the third part. This is the current and voltage sensors that the welding current and voltage are fundamental signals that can be collected during WAM and welding to provide real-time feedback on the process stability and defect formation. So the formation in current and voltage waveforms can detect these things, and these signals are widely used for detecting porosity, burn through, lack of shielding gases, dirty parts, penetration issues, and spatter. So many of these parts can be detected by the current and voltage waveforms. So these can be used by oscilloscope. We can put oscilloscope signals with CMT. You can see here, this is the CMT welding power source, and there's the welding torch. This is the actual process. There's the voltage and current signal feedback. So this is the main part. So this feedback gives the information to the computer signals, and this signals is again changing the weld settings. So if there is a problem in the waveforms, these waveforms, if the different in spikes are forming, so that is that suggests that some of the part is having defects like porosity, burn through, and all. So these defects can be identified. So if we have the key applications are like porosity detection. So that is achieved by analyzing distortion in voltage parameter relationship. If the voltage parameter relationship is distorted, then we assume that there's a porosity detection can be assumed. And voltage signals show if the voltage signal shows irregular patterns or missing segments corresponding to the pore locations and sizes. So that's why so that we can finally conclude that there is some porosity in the fabricated part. So these two things are important. First is the voltage parameter relationship is distorted, and the irregular patterns of the voltage. If these things are showing, then we can tell that this is having the fabricated part is having some porosity problem. And if another defect, if we want to categorize in this thing, is incomplete penetration and humping defect is very common. Like it's a camel hump. If in high heat input parameter, if we are setting, and the humps are created during the layer deposition. So humps is like a camel hump. If these humps are seen, then these are also a defect, that is the aesthetic defects during the VAM fabrication. So that is also not needed. So how we can monitor these things? Monitor using a charge signals. We can use charge sensors to study the plasma charge currents. So if the current and voltage waveforms are having these problems, then we can uh, justify that the fabricated part is having incomplete penetration and humping problem. So other defects is also like geometric or fusion defects and multi-layer VAM monitoring. So there are multiple defects that can be monitored with this current and voltage waveforms. And if there is some misalignment in the weld pool shift, so you can see in the image if these problems are there. So this is the arc on, arc off, and this is the weld pool shift. If the weld pool is shifting, the spike will be identified. So with this spike, we can identify there's a weld pool shift. This is normal welding. You can see in the image. So these spikes, you can see this identifies the weld pool shift. Some misalignment and some geometrical defects can be detected by this. Porosity defects can be detected. So these are the defects that can be detected by current and voltage waveforms. So next is the vision sensors. Vision sensor. So vision sensors are like CNN we are using overall. Like vision sensor uses camera and vision sensors to monitor welding and VAM process. It is attractive because of its high precision. So high precision, fast detection speed, non-contact setup, and relatively low cost. Actually, like vision systems are widely used in weld pool monitoring, seam tracking, defect detection, and process guidance. So there are different types of vision sensing devices, that is passive vision, active vision. So these two are the major vision sensing. There are many more, but these are the important things. So in passive vision, we are assuming like it is similar to human inspection, like with the human eye, how we can identify the visionary defects, that the passive vision is similar to the human inspection, typically using CCD or CMOS camera that captures image of the weld zone to identify defects like pores, grooves, slag inclusion by comparing parameters or through image mapping. So uh, by visionary camera, we basically we are using CCD camera. There's a high speed or slow tracking camera, high speed camera. So that will take the image of the cross section the cross-sectional image has been taken, and then identifying the defects, like if the image is having some porosities, so the image will be identifying these things, say the pores, grooves, and slag inclusions, so that can be matched. Then active vision it is uses auxiliary light sources, that is laser strips, structured lights, and diode lasers, that enables precise measurement of bead geometry, weld seam deviation, and 3D morphology reconstruction. So by passive vision, we are just using the camera, but with active vision, we are using the auxiliary light sources that can detect these things, the precise monitoring of the geometry. So here you can see the CCD camera is here. The camera at 70 degrees checking the real time, capturing the real time image of the weld bead. This image acquisition card is there. Then the data is fed by the computer. Data acquisition card is there. So all these things are related. Then we can justify that these cameras can detect the defects, and it's used for smart manufacturing. So the application part is structured light sensors is the application part, high speed imaging, simple CMOS CCD camera. We can use laser vision sensors. We can use IR cameras are very much used in, I think, every process. IR cameras are used, and in hybrid systems. So these are the examples that we can use for visionary systems or visionary defects detection. But limitations are like there are some limitations for this also, like they are having environmentally sensitivity is one problem because of arc brightness, spatter, and noise affect stability, and computational demand is a limitation. Small defect detection, like many size defects, may be overlooked, like very very tiny porosities can be overlooked by these defects because the accuracy and the camera magnification is not that much if we are using the normal CMOS CCD cameras. But if we take the high resolution or high magnified images, then we can trigger that the different the miniature porosity samples, miniature porosity defects. So in this image you can see the illuminating laser is here. One second. Yeah, here illuminating laser, high speed cameras. So all are moving to the WAM sample. So laser optics are there. So all the data has been collected, and the how we can detect the defects during the real time fabrication of WAM. So these things we can uh, measure. So next is thermal signal based sensing system. So for thermal, we are using infrared cameras, infrared sensors. Basically, I think everyone is well known about the infrared cameras and sensors. Thermal based sensing methods like thermography, infrared emissions, temperature monitoring are widely used for detecting the welding defects, such as wormholes, lack of penetration, lack of fusion, porosity, cracks, deformation. All these can be detected by this thermal based welding defect detection. So first of all, if we are using infrared thermography and emissions, infrared, it can detect weld flaws like wormholes, incomplete penetration can be detected, and lack of fusion can be detected. And with varying welding parameters, shielding gases, electrode, and base metal properties. So that infrared emissions can vary about the process parameters. So temperature sensors like pyrometers, fiber Bragg rating sensors, FBGs that we understand. So these pyrometers and FBG sensors we can use for temperature sensors, because pyrometer is very low cost sensors to monitor melt pool, vapor fume temperatures, useful for detecting incomplete penetration and burn throughs, but limited in detect defect coverage. So these are the very cheap sensors, that pyrometers. Then thermocouples also we can use. Thermocouples are not that much accurate, but we can use to measure the temperature, measure interlayer temperature. But like in between temperature, if we want to measure, then we can use thermal imaging camera also. Like we can set the emissivity at the camera end and the this fabricating end. The emissivity of the material depends, uh, it should be same. Like for aluminum and stainless steel, the emissivity is different. So if we are fabricating aluminum alloy, the emissivity value is, I think, it's around zero point 0.8, I think. And if we are doing stainless steel fabrication, the emissivity value is 0.25 something. If we are setting that emissivity value and we are image capturing the image of the through thermal imaging camera, then the values, accurate temperatures can be measured in between the layers or in the surface of the measurement can be done. So temperature measurement is also an important factor. And thermocouples, that I already told, that it measures interlayer temperatures but often lag actual values due to slow response. Like thermocouples are not that much accurate as compared to thermal imaging camera, that IR cameras and all. So more accurate in high conductivity metals, that thermocouples can be done. And it can be combined with IR cameras to monitor thermal cycles also. So thermocouples can be integrated with IR cameras also. then if we want to move for advanced thermal monitoring, then thermographic line sensors are there. Dual channel filters and CMOS systems integrations are there. So for thermographic line sensors, that enables real time well temperatures tracking and seam width monitoring, minimizing arc disturbances. These can be calculated. So this is the advanced version of thermal imaging cameras. So basic, if we want to have a smart manufacturing, we can use infrared sensors and infrared cameras. That is sufficient. But if we want to have like a best product for, like if we are fabricating a um, very unique product for ISRO or DRDO, the defect percentage is almost like 0%. So defect should not be there. So that's why we are moving for advanced thermal monitoring systems. So that can be done. But for normal fabrication, then we can use normal this infrared cameras and sensors are actually we can do it. So the next is in situ ultrasonic testing in WAM. In situ ultrasonic testing is it's a basically a mode of ultrasonic scanning. It's cost effective, fast, and capable of detecting internal well defects. So you can see here UT probe is placed over here and data acquisition is done here. There's the base metal, molten pool, there's the well direction, flux residues. So as the fabrication of this part is done, this ultrasonic probe detects the data and the data is fed, and the it detects the defects, how much defect, what type of defects is there, or how we can detect it. So you can see here. So ultrasonic testing, why we are using it, is useful for offline inspection also, but at in situ ultrasonic testing UT requires a suitable coupling medium to transmit or receive the sound waves at high temperatures. So because that's why this flux residue is there. So solder flux has been tested as a coupling medium. The solder flux is used as a coupling medium, showing no negative impact on the material properties, though some accuracy is reduced due to heat effects and noise. So this is the coupling medium for UT, and it can be demonstrated ability to detect 2 mm internal defects, that is 100 degrees Celsius, without waiting for cooling. So almost 2 mm internal defects can be detected by UT probe. So here you can see 2 mm, 4 mm, and 6 mm. So other thing is X-ray fluorescence spectrometer, XRF we can use, and that is also a good thing. You can use it detects changes in wire elements composition during VAM fabrication. It uses an X-ray tube, semiconductor based detectors, and laser profilometer to analyze bead size and element fluctuation. So these things we can use to detect these things. So here you can see the image, B image. This is the area of interest, like 40 sample wall. Sample back wall repetition is there. This is the aluminum sample. This is the UT probe, and this is the 15 this thing height. So as the vibrations and this thing ultrasonic probe detects the data, and it can detect up to 2 of this internal defects. So that is the main idea behind this. And then this is schematic diagram of LU inspection, and this is 3D LPI. Okay, so LU is laser ultrasonic testing. LUT is a promising non-contact method for detecting welding defects during fabrication. It is suitable for high temperature and confined environment. So for high temperatures, we generally use these things because other things will be having some problem related to thermal issues. It uses laser, this LUT, laser ultrasonic testing, uses laser beam and interferometer to generate and capture ultrasonic signals, offering high resolution and wide frequency bands. So, to the limitations of these things is low sensitivity in thick walls and challenging from rough VAM surfaces, affecting signal to noise ratio. And LUT can detect internal blowholes, like internal defects can be detected, superficial cracks, and map defects via A scan and C scan imaging. So this system can be uh, LUT system acquire A, B, C scan information of defects, location and resize, reconstruct defect. So defect can be detected, very fine defects can be detected by this also. So it's a advanced version of ultrasonic testing. It is laser assisted ultrasonic inspection. So this is and this can be used for further testing also. In the summarized version, like manufacturing of this is the manufacturing system. This I'm skipping, like topography, image, and all this. I've already discussed pre-processing, image where conversion, these things. So if we are basically summarizing the sensing of technology in VAM, so what we have already discussed the optical thing. So for optical, we are using CCD spectrometer and NIR spectrometer. So where we are using, with the purpose of using, I've already discussed, that is online monitoring and containment and porosity detection, and NIR is used because real-time monitoring, weld perturbation, and defect detection. So these things, if we want, is the purpose, then we can use these kind of optical sensors. The advantages is for CCD spectrometer is real-time, no environmental issue, noise, long working distance, non-contact, more robust and stable. So wide range of wavelengths can be maintained. So it is high. Limitations are also there for every sensing technology. Hard to detect subtle defects, low accuracy in detect inner pores, unable to detect grain size. So these limitations are also there with CCD spectrometer. So if we move to acoustic emission, so briefly we have already discussed microphone and AE sensors. So microphone is the purpose is to use for welding monitoring, defect detection. So it is cheap, simple installation, ability to detect incomplete penetration, misalignment, porosity, spatter, weld irregularities, and the limitations is highly influenced by environmental noise. Install position uh, must be carefully chosen. Some low accuracy data sets also. So for AE emissions, weld health inspection and integrity assessment purposes there, easy to detect slag, porosity, cracks. So depending on the defects, we can choose the sensors that we want to use, and it is not there like only one sensor we can use. We can use the combination of both, like optical also, acoustic also, and many other sensors can be integrated, and multi sensors can be integrated in one system. So that helps in uh, creating a defect free component can be made. Like it's like minimizing the defects at every cost, like for by increasing the feedback and increasing the data sets and increasing the information at the time of fabrication. So by increasing these things, we can almost reduce or mitigate the porosities or slag thing, cracks. Every defects can be minimized. That is not done in the normal or traditional methods. In traditional methods, we check by NDT and destructive techniques we are using, and after fabrication only we are getting to know about these defects. But prior to fabrication or during fabrication, how the defects can be uh, checked and minimized and mitigate, these things can be done with the sensors itself and the multi sensors we can use. So not only one sensors, couple of sensors or many sensors we can integrate in one system. Okay, so current and voltage sensors we have already discussed: charge sensor, Hall effect sensor, magneto-strictive sensors. In this charge sensors, it is the purpose is to weld is for welding monitoring and defect detection. This is also for defect detection. This is for real-time monitoring. So for humping, we are using charge sensors. If we have humping defect or we see the humps, then charge sensors can be easily used. It's a cheap way to detect humps, humping, and incomplete penetration in laser welding. And Hall effect sensor is able to detect humping and porosity, high frequency data acquisition system. And for magnetostrictive, it's non-contactive measurement stress waves, able to inspect large structures, defects, internal holes. So these advantages and limitations are there. So whoever wants to integrate these sensors and in your traditional machines, you can check the stable, and the stable is very important. So that this can you can check the advantages, what defects can be detected by a specific sensor, and that you can integrate. So coming to vision sensors, we can have the structure light vision sensors, digital cameras, high speed cameras that I've already told you. So real time defect detection can be done, able to detect the weld bead misalignment. If misalignment is there, that can be detected by structure light, mismatch and undercut, reducing welding noise, non-contact. These things can be done. And with high speed camera, not influenced by brightness during WAM, abundant information. So uh, light and brightness is not a problem for high speed cameras. It detects the fluctuation effect in WAM process. So for thermal, we can use IR sensors, IR cameras, thermocouple, pyrometers. These things we can use, and uh, the purpose are listed here. Infrared sensors used to monitor the weld pool, IR camera for thermal analysis, thermocouple for interlayer temperature measurement, pyrometer is for welding defect detection. So these things these advantages we can check out, and these sensors we can integrate. So other sensors means ultrasonic testing, X-ray fluorescence, spectrometer, laser ultrasonic testing, LUT, and 3D laser profilometer inspection. These things I've already discussed in the previous slides. So in situ inspection of defects like porosity, overlap, cracking. For ultrasonic testing, we are this purpose is this, and it suits most offline inspection cases: accurate, accessible, cheap, easy to incomplete, easy to implement. Sorry. For X-ray fluorescence, the process measurement of the chemical composition is there, and it can inspect extra large structures, sensitive, and many more. And for laser ultrasonic testing, defect detection is the main purpose to use. It saves time and cost, can bear rising temperatures, small working space, useful for internal holes and surface cracks. And for 3D laser profilometer, in situ surface detection, defects detection is there. So in situ means like we are actually using uh, two or three sensors, and with profilometer we are using during the fabrication process. So it locates the identify and identify surface defects quantitatively. It detects both large and small scale defects, effective and efficient. So these advantages and limitations you can list down, and depending on these things, you can identify the number of sensors, types of sensors, what you want to integrate in your traditional machines to upgrade your machines to a smart manufacturing. So these things can be done easily, and for lower cost, you can easily maintain that. For low cost sensors, if they are available, then you can easily add these things to your system to upgrade and get a defect free final products. So moving to the second main application integration part of smart manufacturing into AM is digital twins and simulation. And digital twins and simulation, I think many lectures have been already done for digital twins, and I think Janoop sir has taken digital twins, and many other have already talked about. So I'll be briefly explaining this. So digital model replicate AM process virtually. So we have the virtual reality and augmented reality here, VR and AR form, and there's a mixed reality that combines the VR and AR. The mixed reality means that combination of virtual reality and the augmented reality. So it predicts process outcomes before actual fabrication. It helps in optimizing the path planning, deposition, and thermal control. So digital twins and simulation is very important factor for uh, adopting for smart manufacturing. So this is the WAM digital twins and visualization. You can see here. This is the visualization part, data collection, simulation, and then digital twin environment. So the actual lab can be digitally uh, twin can be digitally twinned on your system or on your phone itself, and you can easily get to know the information about what process parameters are currently running without going to the lab itself. By sitting in your cabin itself, you can use your phone and you can digitally twin your lab, and you can integrate these things to actually capture the process parameter also on your phone itself, and during fabrication what current voltage values are changing in the real time. So that data also is fed into the in your system or your mobile phones. This can be connected to your mobile phones also. So all the digital information that is actually happening, that can be uh, easily fed to your systems. So challenges, I think, for additive manufacturing, if we are focusing on WAM, so challenges in WAM data is it is having a complex relationship between material properties, design, process parameters, post processing, and final product quality. So the relationship is very complex. So WAM often lacks robustness and repeatability. So for example, if we are optimizing a process parameter, suppose if we are fixing current values, voltage, wire feed rate, travel speed, gas flow rate, so all the input parameters, if we have controlled and identify the best and dominant process parameters, and we have list down the dominant factors, and we have fabricated as per the design of experiment and other approaches, as we have done the experiments. But after fabrication and the real time data sets and the mechanical strength, if we want to calculate as per the strength, wear data, corrosion data, so these things, if we are calculating and we are optimizing the process parameter on the basis of that output. So by optimizing the process parameters, and if we found out that one process parameter is optimized, and if we are repeating that process parameters, and if we are I think like if we are um, repeating like the same process parameter, if we are again doing it in the real time real thing, so it may occur like the difference and repeatability issues can come in the WAM process. So it's not like if we have got the one set of process parameter, and if we have fabricated a component, it doesn't it it doesn't happen like if we are fabricating again with the same process parameter, we can't we can have some repeatability issues or some internal defects issues, some problem can be happen. So that accuracy and that repeatability to achieve in WAM is very important. If we achieve that repeatability and robustness, that is the major issue in WAM, because repeating itself is a problem. But only repeating the component, then only we can justify that these process parameters and these output can be achieved again and again, and that can be fed into the industry, and these parameters can be used locally, or the industrial application can be done. So that accuracy and repeatability has to be maintained. So there's a need for data management also. If effective data management system can reduce development time, cost, and defects while improving the quality. Key equipments are like easy access to complete product knowledge, traceability of product information, automation, and information flow. So these things are the data management sets, because data management is very important. Like for data collection, these scanners, thermal cameras, welding cameras, all the data collected, all the data are collected from here. So the role of digital twin, why digital twin is needed? The role of digital twin is act as a bridge between the cyberspace and the physical space, that is enabling advanced data analysis and process control. So it bridges that gap between the actual experimental thing and the cloud computing part of thing. So that cyberspace and physical space, that thing has been bridged due to the help of digital twins. So it extends functional and coverage, scalability, and accessibility also. It collects, manages, and reanalyze data to enhance repeatability. So, without digital twins and visualization, I think repeatability is a main concern in WAM. But by integrating digital twins and checking the real-time monitoring and collecting the data sets, simulating it, manages and reanalyze the data, that enhances the repeatability and producibility and quality assurance in WAM. So these things are very important for uh, WAM sustainability, like repeating itself. because without repeating, no experiment is viable. So digital twin supports simulation of microstructure and residual stresses also. Here you can see the simulation, and if we are laying over the beads, this is the TIG torch, and you can see at one position the grain structures, grain refinement is there, flow field of melt pool is given. So these data can be achieved real time. So it supports simulation also in the microstructure, and majorly it is residual stresses that is a concerning factor. So by digital twins, this also can be maintained. So this is very good to implement. It helping in guiding and optimize process parameters also. So where residual stresses are more, and suppose it is a tensile residual stress, and that is detrimental to the WAM component, as tensile residual stresses will increase the possibility of delamination. So two layers can be delaminated by increasing by having tensile residual stresses. So these things can be maintained and kept at a minimized thing. Like if residual stress can be reduced by just in the real time data collection and real time monitoring and feedback, so that process parameters we can avoid, and the best parameters can be done. So digital twins also relies on physics based simulation for adaptive and automated controlled decisions. So it is also physics related thing, like the droplet, the arc stability and droplet detachment. These physics of droplet molten pool is also necessary, because to analyzing the flow field of molten pool, you can see because of this also we can verify the residual stresses in between the layers. Uh, so next is WAM system framework based on digital twin. This is the system framework. So uh, I think many of you will be knowing that digital twins, digital twin is a new end word in the market, but it is first proposed in 2002. So it is not a new concept, new word. It was in the market, but now it is booming, booming in the smart manufacturing field, like digital twinning, actual and virtual reality. These things were already there, but it was not that time of booming. But now it is like on the hands of everything, like digital twins and machine learning. Everything we are using. In WAM, it must digital twin must address the multi-step processes, refinement, and real-time monitoring. You can see here the framework is aligned like this: process planning, process monitoring, quality measurement, and result prediction. So these things I've already discussed in the first slide itself. So how this digital twin is affecting the smart manufacturing, using smart manufacturing, how the digital twin is affecting the WAM system. That is the main output of this slide. So these are the things, like suppose these are the digital twins functions: data collection, data management, data processing, simulation, forecast, and automatic decision. So for data collection, we collect real-time process data. That is the real-time data collection of molten pool flow, geometry, surface characteristics, and thermal mapping. So the actual data can be collected through the data collection mode. This thing. And this relies on IoT and sensors. This data collection, how we are collecting it because of the IoT and sensors to capture the WAM physical state forms the foundation of higher level functions. So as the data is collected, then we have to manage it. How the data is managed, like WAM generates large volume of design, process, post processing and quality data. So only selected and reusable data improves WAM efficiency. So it's not like that that WAM is giving only one or two or more than 10 or 20 data. It's like a large volume, means 100 data sets can be measured by this WAM, one component of WAM. So all the data are not usable, but only selected and reusable data improves the WAM efficiency. So we are using all the data, but the selected parameters or selected data is only important for the quality of WAM, not all data. So for data management, we are using cloud and edge computing that manages data disorganization, support reuse of historical and plus real-time data can be managed. So it enables efficient simulation, prediction, and process optimization. So this part is done by data management. Then we move forward to data processing. So it transforms raw data into usable and meaningful information. So this is having only collection, this is management, and the processing part is transforming the data, raw data, into a meaningful information. So raw data is not needed every time, but the raw data is transformed into some meaningful information that is to be utilized for improving the quality of WAM. So that is important. So this step is very important. Data processing, so which data to neglect, which data to use, that is the role of using data processing. So data processing handles computationally heavy WAM processes like heat transfer, melt pool, stresses. All the computational processing is done, like heat transfer equations, melt pool equations, sensor stress analysis. Everything can be computationally processed. And using AI and ML, many nowadays AI ML is very common. So how the data can be transformed using, we can use AI ML methods like CNN, SVM, DL, that is used to detect patterns, improve quality inspection, and optimizing the control. So it gives the foundation to operation, control, and prediction. So the next step is simulation. Simulation we have already discussed. It's builds on the virtual model to replicate WAM behavior. So actually simulation is like we already know, before like actual fabrication, we can simulate the data sets and we can actually know what kind of defect can be occur in future, or the with these data sets or these parameters, what kind of defects can be detected or what kind of defects can be occurring. So with traditional methods like finite element simulation of temperatures, FEM, everybody is knowing about finite element method. So these simulations, like it is doing simulation in temperature, stresses, and residual stresses. That is the traditional method. But nowadays, advanced methods have come, like iterating substructure, mesh refinement, GPU based FEM for high fidelity. So technology is transforming, like it's booming like 0 to 100. So FEM is already a very good method for simulation, but nowadays advanced version of FEM is also uh, in the market, like GPU based FEM for high fidelity. So simulation, um, after simulation it is forecast. So it is like a prediction. Forecast is prediction, forecasting system behavior, equipment states, and defect probabilities. It Forecasters forecast all the things and enables real-time optimization, correct certain and uncertain data, contradictory data, minimizing defects during fabrication and design. It ensures continuous feedback between physical and virtual twins for process improvement. So it is basically a forecasting the parametric data. And the last is automatic decisions. So it is the most challenging and critical layers, because if we have done everything like collection, management, data processing, simulation, forecast, the last step is decision making. So decision making is all, it's like a challenging situation. So what parameters have to be considered, what things have to be ignored, these things are very important. So decision making replaces or assists technicians in making optimal process decisions. It balances trade-offs. It is still in the early development. Automatic decision is in the early developments. So it is not uh, completely widespread. So still it is going on. Maybe the technology is booming. It will be coming in the future. So it's the future. Smart manufacturing is the future for manufacturing systems. Oh, so here we can you see the visualization of for WAM digital twins. You can see here VR, AR, visualizing immersive virtual scene, low scene of reality, digital twins, cloud digital twins. MR is the mixed reality, visualization, unintuitive WAM experiences, visualization, multi-party collaboration, fully realized digital twin for functions. Just a minute. So why we need visualization for WAM digital twins? So basically with Industry 4.0, WAM research emphasis advanced visualization to improve machine interaction, data accessibility, and human computer interaction. So visualization enhances efficiency, collaboration, and inclusivity in manufacturing. So this is why we need visualization. So without this, it is tough to do these things. So limitations of traditional methods are there. The traditional methods limitations are conventional visualization tools that we are using already that lacks portability, interactivity. Advanced visualization through VR, AR, MR is required to fully represent WAM digital twins. So the traditional visualization that we are using, that lacks portability. So at the site visualization, that is not possible. But with the advanced VR, AR setup, like with in your AC rooms and AC cabins, you can easily check what is going on in the augmented AR and VR. So the in real time situation, what is the actual visualization you can see on your phones. So these things is integrated, and this is very important. So virtual reality, it's create this VR. This is VR is the virtual reality. It creates immersive training environments for operators, designers, and consumers. So it is useful for education, technical communication, and familiarization with WAM. It helps simulate settings, reduce misunderstandings, and train without high cost. And limitation of VR is that not it is not ideal for visualizing digital twin function. It is not the ideal method. So AR is also there, augmented reality. It adds digital overlay to real world WAM processes. It enables 3D model interaction, rapid design validation, and the feedback mechanisms. And it is useful in training, teaching, and maintenance tasks also. And the limitation of AR is still a large gap in fully realizing the digital twin functionality for WAM. So there is a gap between the augmented reality and virtual reality. So both is having some limitations. So we are combining these two things for mixed reality. So this is also a thing, a mixed reality. It is best suited for WAM digital twin as it merges both the digital aspects and the physical aspects. So the all the real time aspects can be integrated and it is merging with the digital aspects. So both the function, both the features of VR and AR are there in MR. That is the mixed reality. So um, in the recent papers, some many of the researchers are working on MR mixed reality, are uh, justifying that this is the best suited for WAM digital twin. So it is also proved that we are using MR for WAM, and it is creating very good combinations, very good product, and visualization is very good. And this MR enables interactive monitoring, remote collaborations, and design validation. It supports tactical feedback also, enhanced visualization, and gesture-based controls also. So, like your phones, you can use these things. So, technology is this much ahead. So, it's the MR mixed reality for WAM digital twins. This I have already discussed. This is the gesture based recognition. You can see with your fingertips, you can visualize, zoom out, flick, right swipe, left swipe, uh, rotate, everything you can do with the gestures on your phones, and you can control all the factors that is having that is practically doing in the real time environments. So the coming to the third part, this is the third important step for smart manufacturing. We have completed two things, and this is data analytics and ML. This is the booming stage of ML. So data analytics and machine learning is very important. It analyzes the sensors data. So in the first step, we have set the sensors. All the sensors have been set, and we have uh, done the data collection also, everything we have done. But this is the time for analyzing all the sensors data. This is known as data analytics. So to detect abnormalities in real time, so real time monitoring how the data has been analyzed. So the analysis part has been integrated in this points. And the ML part. ML model recommend optimal process parameters. These are the input process parameters: current, voltage, wire feed speed, and travel speed. So for ML model, these are the input parameters, and how the data can be analyzed and reused for uh, getting a very good WAM product. This is the aim for this. So it enables predictive maintenance and adaptive manufacturing also. This is very common terms now. So machine learning in WAM, the role of machine learning in defect prediction and classification. Data types used is image data, signal data, hybrid data. Image data is vision based, signal data voltage and current, sound, and hybrid data is used for like combination of these things. Insert flowchart like WAM, sensors, data, ML model, defect detection. This is the basic flowchart that we follow. And these are the ML techniques. So first is supervised learning, SVM, decision trees, neural networks. Unsupervised learning is cluster of anomaly detection. Deep learning, CNNs for image-based defect clarification. There are many papers there are that is based on this deep learning. So if you search for WAM, many of the researchers are working in this field, deep learning. So they're using the image-based software, and like this type of images there, suppose Suppose if we are using the weld bead optimization, so where the VAM is having porosities, undercuts, and other abnormalities. So there can be many defects like over penetration also, lack of reinforcement, lack of fusion. So not only one defect is there, multiple defects can also be classified and we can sort in a way like this is first detrimental stage, second detrimental stage, like which defect has to be cleared first, like what is the priority order of the defects. Suppose porosity is the major uh, important thing, so this is having highest priority, so we are giving 3 star to this. And suppose if we are having the other defects like lack of fusion, delamination, the it depends on the criteria, which criteria we are following and which image based system we are following. So if we are having many defects in a single image, so we can classify the defects and we can sort also as per the characterized defects. What is the defect characteristics, so that we can do, and we can eliminate these things using the optimized process parameters. We can mitigate these things by integrate these sensors feedback things we can analyze, and after analyzing we can change these things. So this is the predictive things that we check. So this slide is very important. So this is showing the machine learning application in WAM defect detection. So what are the machine learning models that has been done and now till now is these models you can see the CNN is there, SVM, many models are there. You can see here. So basically SVM is support vector machine, and RF is also there here somewhere. Yeah, there is RF means random forest. That is the traditional machine learning softwares, machine learning approaches that uh, SVM and RF that detect defect. It uh, gives the defect classification and recognition. So it's common in traditional method that is only giving this SVM is only giving the defect classification, what is the type of defect it is. By showing the image we can classify the defects and the recognition of defect. So the image only gives the name of the defect and the recognition only. So by uh, one more model like BP, this is back propagation. So back propagation gives the process parameter prediction and optimization. So this SVM, RF, and BP are the traditional field of ML approaches, machine learning approaches. But nowadays, people are going for deep learning that I have already told. CNN CNN is convolutional neural networks that gives the direct image analysis for defect detection. No manual feature extraction is there. So it gives the direct image analysis. What are the types of defects is there in the image, the sorting of the defects, and all the defects is detected in single step. No manual feature is used. And similarly, RNN is also there. Here you can see RNN here somewhere. Yeah. So RNN is also there. That is recurrent neural network that helps in sequencing the data and time series analysis. So these things has to be integrated. And one more is there, that is GAN. GAN is the generative adversarial networks, that is helps in data augmentation and anomaly detection. So these deep learning approaches, if we use CNN, RNN, and GN, then we can directly do the image detection by defect detections, and it can be sequenced it in the time series, and we can get the data augmentations ready. So, what are the application in WAM? If we are focusing in WAM only, we are not doing the complete additive manufacturing. We are focusing in the WAM, what approaches and what are the applications. So, data pre-processing is important. Defect recognition and classification is very important. Process monitoring in real time is the third thing. Prediction is also there, and the last is optimizing of process parameters. So these are important in WAM as we are doing the WAM 3D components. So these are very important. So by using the approaches, we can uh, quantify it and we can make it. So next is the machine learning model architecture. You can see here data processing, defect detection, prediction. So this is based on CNN, SVM, RNN, SAE. These are all the machine learning approaches. DBN, LSTM, CGAN. So all the approaches are this advanced. These are the advanced approaches that machine learning approaches that uses data pre-processing, prediction, and defect location. So all the things is in the advanced version. Hmm. So data pre-processing, coming to this data pre-processing, it's specially denoising. It is specially denoising, advanced feature extraction, and augmentation. It is vital for robust WAM defect detection. So data pre-processing. So combining wavelet-based models, methods like ML and DL models enhances accuracy, reduces noise impact, and improves model generalization. These things can be integrated and we can improve the ML model and we can get a very good WAM product. So all the things are used for improving the quality of WAM only. So how the defect can be minimized or mitigation, that is the prime objective of these all models. Hello.
sir.
So is there break in between or I have to continue till 6:30, like 1 hour? Hello, Vishal.
सर 5 मिनट का कर सकते हैं ब्रेक चाहे तो.
Uh, okay, like
है ना.
if
सर 5:40 हो रहा है ना. 5:50 पे वापस रिज्यूम कर लेंगे. 10 मिनट
yeah,
का
for
ब्रेक करेंगे.
5 minutes, after 5 minutes, we can continue.
ओके. ओके.
Okay, sir. Okay.
Participants, there is a break of 5 minutes. We'll meet again 5:45.
Hello?
Yes, sir. We can resume again.
Yeah, yeah. Sir. Thank you for the break, sir.
Okay, okay.
The slides are visible, sir?
Yes, it is.
Yeah. So we were talking about the data pre-processing. Data pre-processing basically it converts raw sensor data into a suitable input for ML models. So every model is having data pre-processing. So depending on the different types of ML model we are using, so data pre-processing converts the raw data that was collected from the data collection systems, and it is converted into the suitable models, specifically like if we are using CNN. So data pre-processing converts that into the CNN readable format. So it includes denoising, feature extraction, data labeling, and augmentation. So if we are going deep inside denoising methods, like it is wavelet transforms, improved wavelet thresholding, that is very complex things. So I'm skipping that thing. So coming to CNN model, CNN based model, this is very important. CNN automatically extracts features without manual pre-processing. It is compared to different types of CNN models, and like it is having higher robustness and lower error, fewer iterations also. Like minimum iteration, with minimum iteration we can achieve a best combination of the uh, achievement, like defect detection. We can achieve quickly like what is the defects and what is the quantity of defect, so that we can uh, figure out. So next is SVM. SVM is the B part, that is support vector machine. It is effective for classifying simple defects such as slag, porosities, and incomplete penetration. These kind of defects are simple in WAM, that is common defects. So it is effective. This approach is effective for these simple defects. It relies on handcrafted features, like it is less effective than CNN, but multi-sensor fusion or high-level features can be used. So CNN, as compared to CNN, SVM is not that much accurate or not that much effective. So we can compare these things. Then the next is RNN. RNN handles sequential time series data. RNN, it is can learn temporal relationship but suffer from vanishing gradients. So these things are also there. RNN, other deep learning approaches are also there. So there are multiple things. Everything, the important ML models are basically CNN and then SVM. So these you can characterize. So what are the advantages for using ML and WAM is we can go for real-time monitoring, automated classification, reduced, that is human error. We can reduce human error, and we can have a higher scalability for large scale parts. For industry purposes, we can increase the scalability. So these all things what we are doing by integrating the sensors, data collection, data processing, data analysis. So all the things are for the industry. The final verdict, final thing has to be given to the industry 4.0 or improving industry 5.0. Like the collaboration between the research and industry, that is to be made. So these things can integrate and give a best type of model. What is the best type of model as per the different types of defects, and that can be given to the industry, and that is the level, high scalability level that we can achieve for reduced or minimized defect products, or WAM products can be fabricated by industries. So that is the major output. So integration with digital twins and smart factories are also there in the advantages of ML and WAM. So the fourth thing we have reach the fourth aspect of smart manufacturing is Industry 4.0 integration. So everybody is knowing about Industry 4.0 nowadays. People are talking about Industry 5.0 also. So collaboration between 5.0, 4.0. So what it actually means that we can understand with these slides. So this is IoT enabled AM machine communication, communicate across supply chain, cloud platform support, remote monitoring, and process sharing. Blockchain ensures part traceability and certification. So, Industry 4.0 integration in VAM uses digital technologies like digital twins and machine learning that we have already discussed, DT and ML. What DT is coming, what DT is giving for the VAM, and what ML is doing for VAM. So by integrating DT and ML, digital twins and machine learning, for enhanced monitoring control, optimization of VAM process, thereby improving automation, intelligence, and manufacturing quality through real-time data collection and analysis. So Industry 4.0, what is the integration is mainly due to DT and ML. So that is the Industry 4.0 needs. So this is the highlight of Industry 4.0 and Industry 5.0. So Industry 4.0 focuses on connecting machines. So there are number of machines. Suppose there are n number of machines are there. So the integration between all the machine, and there is a central computer set is there. If we command through a central computer, all the machine will be fabricating the same component in the bulk order. So for mass production, it is very much needed. So it is for mass customization, intelligent supply chain, smart products, manpower distanced from factories. So what is the transformation from Industry 4.0 to Industry 5.0 is focuses on delivering customer experience. So till now we are just fabricating for a high scalability order. 4.0 means mass production, mass customization, everything like uh, multiple CNCs or multiple robots can be connected in a single order, or multiple robots can be connected with a centralized computer, centralized system. That centralized system gives the command to all the respective machines, and the mass production can be done. So but now for Industry 5.2, what are the transformation that is done is it is focused on delivering the customer experience. So customer is the main the output dealer. So with that experience, like customer satisfaction is done, hyper customization can be done, responsive and distributed supply chain experience, activated products, return of manpower to factories. So Industry 5.0 is giving the opportunity to having a variety of products and customer satisfaction. So customer is the end user. So end user has to be satisfied by using Industry 5.0, or by using this by using DTML, by integrating these things, and the final product is uh, for the user, for the end user. So customer has to be satisfied. So that is the main goal of 5.0. So main is 3D printing, like VAM we are using as transformed industries. We are all we are knowing that Industry 5.0 emerges as the response, emphasizing human machine collaboration. So human machine collaboration means it is nowadays industries are having cobots also. It is a collaborative robots. So what is human machine collaboration? It values human creativity alongside machine precision, supported by collaborative robots. So collaborative robots, the terminology is cobots, 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 that handle repetitive or heavy tasks. So it is the integration of human and the industry. So human integration and human and machine integration. forms that cobot system. So many industries in real industries are having now cobot systems also. You can visit on their websites and cobots, you can figure out that thing. So that is the concept made from industry 5.0, the collaboration between human and machine. So this industry 5.0, it has a model enhanced productivity, innovation and job satisfaction while promoting sustainability and resilience. So example I can give, like, it includes BMW use of cobots in assembly, and the fashion industry use AM with AI driven optimization to reduce waste and speed up design cycles. So BMWs are also using cobots. um, so high end industries are using this industry 5.0 to give a customer, the end user, best satisfaction, that what they're paying for, like that the value for money. That is the main thing. So together industry 4.0 and 5.0 complement each other. Industry 4.0 drives the automation part and efficiency, while industry 5.0 ensures human creativity. So 4.0 was, I told you that it is all about automation, so everything is automated. So nothing is like manual thing, and human intervention is not needed, but all the things on robotics and automation has been done. But for industry 5.0, human creativity is also having the weightage. So human creativity and the mass production, or industry 4.0 or 5.0 integration gives the best results. Like with the human creativity you can make an automized and best product also. So it is having, their integration shapes the future of intelligence, efficient and human centered manufacturing. So this terminology is very important: human centered manufacturing. So human centered means the creativity of human and the power of automation, so both are integrated to give the human centered manufacturing. So this is the implementation of AM in Industry 4.0 and 5.0, additive manufacturing. So this is efficiency and precision, human role, innovation, sustainability, customization. So basically, Industry 5.0 promotes human-centered and holistic approach where human creativity and machine precision work together to build sustainable, resilient, and innovative manufacturing systems. So it emphasizes worker well-being, ecological responsibility is also there, and broader society goals beyond economic growth, aiming for super smart and sustainable society. So it is human centered, but it is based on industry 4.0, so that integration is there. So so VAM plays a very crucial role in both industry 4.0 and 5.0, aligning with their principles through digital integration, real-time monitoring, data-driven optimization, and customization. So as a part of smart manufacturing, VAM leverages like IoT, AI, big data, cyber physical systems to enable efficient, adaptable, and precision production. So everything is there. So the uh, integration of AM with the industry for 5.0 enhances that efficiency, sustainability, human roles. So but if we are using only industry 4.0, the human role was missing. So but the integration of human thing developed that industry 5.0, and it is having more efficient production, sustainability, and the human roles are giving the weightage, and that innovation, the human innovation compared to industry 4.0, making it a cornerstone for future human centric and smart manufacturing. So this is the relationship between AM and sorry, it is industry 5.0. So additive manufacturing, environmental sustainability, and human centered technologies, HCT. Additive manufacturing basically VAM enhances smart manufacturing by integrating digital tools like IoT, AI, big data, and digital twins. So these are the integrating digital tools. So these enables real-time monitoring, adaptive control, predictive maintenance, and life cycle management, reducing waste and ensuring sustainability. So sustainability is also an important word, and it is an important factor in the later slides also. Sustainability is a big important role, having important role not only in industry for 5.2, it is having sustainability for economic balance also. So VAM supports distributed and just in time production, that is JIT, just in time production, lowering inventory and transportation costs while enabling on demand customer parts. These things are done by Japanese things, JIT, just in time production. So the buffer system has been reduced, like lowering the inventory and transportation costs, so that satisfy the customers, and the online on demand uh, customer satisfaction is there. So within Industry 5.0, additive manufacturing is elevated by human machine collaboration, mass customization, and ecological values. So AI powered design optimization creates lighter, stronger, and more efficient parts tailored to specific needs. So as per needs, we can fabricate all the components as per lighter, stronger, and the efficiency of the parts can be tailored. So real-time data integration ensures seamless operation, predictive maintenance, and automated post-processing. This holistic approach, that holistic approach connects AM with human-centric technologies, that is HCT. That is the most uh, viable term in this relationship. HCT, that is human-centric technology and environmental sustainability. So both are very important as we connect with the Industry 5.0. So this is the co-occurrence map for Industry 4.0 and 5.0 in the additive manufacturing technology. So you can see the center nodes here. 4.0, Industry 4.0 is there. This is additive manufacturing. There is IoT, and there are many other things are also there. So center nodes are Industry 4.0 and additive manufacturing that emerges as super node. So this the node width is more. The thick diameter of node is more for additive manufacturing and industry. Other things are just in like small dots like of thing. You can see selective laser, digital twin, simulation, lean manufacturing, everything. Sustainability is also smaller as compared to this additive manufacturing term in Industry 4.0. So this is known as supernodes, reflecting their pivotal role in modern manufacturing research. So all of the research are uh, integrated with this additive manufacturing Industry 4.0 and Industry 5.0. So every person is working on this only. So they link diverse technologies and processes from IoT and cybersecurity to laser powder bed fusion and metal additive manufacturing also. So the next step, the fifth, is the automation and robotics. So this is a very important thing, because while fabrication we can't use manual efforts. We have to make a automated version, like robots and CNC systems can be used as compared to robots. CNC systems like 3 axis or 4 5 axis. If we use 5 axis robot or 3 axis CNC systems, that CNC systems lacks that accuracy. 3 axis CNC system lacks that accuracy and the precision value. So the accuracy can be like it is in point 0.5 mm accuracy will be there, like. But with the robots, that we can achieve in like point 0.1, like 500 microns accurate product can be achieved. That is for high level near net chip product can be fabricated. So that thing can be integrated because robots are very important. So robotic arm enables WAM for large and complex geometries. Automated pre-processing and post-processing reduces manual work, ensures repeatability and quality consistency. Automation and robotics are essential for WAM, enabling cost-efficient, high deposition rate production of large, complex metal parts with high precision. Robotics are used for controlling the precise path of the welding torch, while automation systems manage power sources, wire feed speed, and process monitoring. So advanced robotic WAM. Nowadays, advanced robotic WAM is used, includes multi-robot systems for increased productivity, closed-loop sensor feedback for real-time adjustment, and integrated in-process non-destructive evaluation also to detect defect detection during production. So advanced robotic WAM is also there in the market. You can see this. These are the KUKA robots that helps in the fabrication of WAM component. So it's a WAM workshop KR90 plus KP2 with the CMT torch. You can see this is the CMT machine that we have already discussed in the morning session. What is CMT? And the B part is KR100 with plasma torch. So in this CMT torch is there, in this plasma torch is there. So, with the help of robots, we can use the different types of primitive trajectories like line raster, line zigzag, circle zigzag, everything we can manipulate. So, it is not an easy method with a manual fabrication. Only with robot, it is acceptable. The accuracy of lines you can see, the precision of the lines you can measure, like the defect is the misorientation will be very less. So modified version of ROS package KUKA experimental robots are used in this case study. It enables implementing managing robots controls through hardware interface that connects robot hardware. Okay, so this is the IWAM. This is I means intelligent robotic WAM. So you can see this component can be this A thing is plasma deposition using IWAM, single bead overlay pads and pad cross section. This is the cross sectional view. Experiments using IWAM advanced, that is CMT deposition on a steel tube. You can see this schematic experiment or table tilted. You can see. So this is the concept of different experiments. In this in this case study, we are using KR10 robot. This one with plasma thing. So this is done by plasma. This is done by CMT. So in this experiment, KR10 robot were used uh, and single bead were deposited via IWAM. Travel speed and wire feed speed were varied in the mid bead to study effect on the bead width, height, and penetration. So the values are recorded like bead width, high reinforcement, penetration, and the width. All the three factors have been noted. The best parameters were used to build a part for two overlaid paths. So cross-sectional analysis was performed and the macro properties cross-section has been cut and we can examine this. So the similarly second case, this is the second case. This in this we are using KR90 plus KP2 robotic cell plus Fronius CMT advanced 4000 hour power source. So this machine KUKA robot is integrated with CMT advanced 4000 hour power source. IWAM advanced was used to test the motion control strategy, and the steel cylinder deposition 10 layers and 5 beads. So there is 10 layers has been made. This you can see in the circular tubular sections, and this also. So steel cylinder deposition, 10 layers and 5 beads with torch orientation maintained towards the surface, normal and gravity. So additional trials included tilting of the table to study the gravity effect on the molten pool spread. So the results were there that the sinusoidal deposition trajectory showed position error less than 1 mm. So the accuracy of this robot was very good. That it is within the tolerance level of the CMT, and the synchronization of signals, wire feed speed, arc voltage, and arc current and voltage allowed easy plotting with external tools. So this can be easily fabricated. So next is sustainability and resource efficiency. That is having smart control minimizes energy and material wastage. Real-time defect correction reduces scrap parts. Support recycling and circular economy models. Sustainability in VAM is achieved through optimized material use via design optimization, cycled material utilization, and on-demand production, which reduces waste and transportation. VAM's high material efficiency, faster build rates, but this we have already discussed. Efficiency, build rates, potential for reduced tool also contribute to better source efficiency compared to conventional methods. Future advancement, particularly in plasma-based and multi-axis VAM systems, promise even lower environmental impacts, highlighting VAM's role in sustainable large-scale metal production. So this is a case study part used for assessing the performance of the process-based cost model. So this is process-based cost model. If we are fabricating a component with a VAM, and this is the fabrication part, and this is after machining what we have achieved. So it is both additive and subtractive manufacturing. So additive, we have done this, and after subtracting what we have got. So it is the process-based cost model to evaluate economic and environmental performance of VAM. The case study focused on producing a stainless steel case study part. The cost analysis is the important factor here. Sensitivity analysis, economic viability, environmental viability also. So like everything we have to discuss for cost estimation. So this is the output of the cost performance of metal deposition stages in VAM processing chain. So this green color shows the equipment cost, then building cost, material cost, labor and energy. All the cost is given in the euros. So this is the equipment cost, this building cost, this is material cost, and this is labor cost. So material cost is very expensive. You can see high amount of material cost. So total cost is this much, and you can categorize as variable cost and fixed cost. And this is the material cost. The material is how much material cost is been separated. So 72% of this material cost of this 21.72 thing euros is gone for wire. So wire purchasing is an important thing. Wire cost is important. Then the 11% goes towards the base metal, then gas and rejection rates. So these are also there. So all this material wastage is also there, but it is very small as compared to other things. If we compare this cost with the laser powder bed fusion, actually laser powder bed fusion is using powder as a raw material, whereas in VAM we are having a wire. So wire is very cost effective. Like for 1 kg of wire, we can purchase it as 2 or 3,000 rupees for a specific material. Suppose if we want to buy inconel alloy or pneumonic alloy or uh, chromium wire, so it can come around 2 to 3,000 per kg. Okay, so but in terms of powder, the cost is increasing in an exponential direction. So for the cost of 1 kg of powders are almost 60 to 70,000. So 70,000 if we take for 1 kg, so that is the major cost. Material cost is the main cost for fabrication of VAM component, not only for the VAM. It the material cost is happening in laser powder bed fusion also. So total cost is this much, 25.84, and variable cost dominates, that is 23.222. That is almost 90% of the total cost. That is the variable cost. Fixed cost is very less. That is the equipment and building cost. Material expense is too much. And then we come to the cost performance of machining stage. This is the depositing stage that we have discussed. This is the cost made in the fabrication part. So this is the cost performance in machining. So for machining, that is the subtractive manufacturing. So this 7.89 euros goes for equipment. This is for building. This is for labor, then energy, then variable cost is this much, and fixed cost is very high, 10.16. So equipment cost in machining are mainly driven by machine acquisition cost, that is 77%, especially for CNC machining centers. CNC machining is very costly thing. Compared to VAM deposition, machining also shows higher building, labor, and energy cost, that is large machine size, greater work involvement, and higher power consumption. So equipment cost, you can see here, 77% of the machine, then tooling and maintenance. So this is the equipment cost, total cost for machining 13.50. And then we compare the cost performance of the complete VAM processing chains with distributions of the individual and the total cost per part. So equipment, building, material, labor, energy, that is this is for individual and this is for total fixed and variable cost. So comparison of cost uh, per part between VAM a processing chain and traditional subtractive approach machining is, this is a part is for individual cost, this is for total cost. So you can see here equipment, building, material, equipment, building, labor, and energy all are very less as in VAM, but this material is very expensive in both as VAM and machining. And compared to this fixed cost and variable cost, you can see 59.41 euros. That is for machining this thing, variable cost, and this is the fixed cost. You can see here additive, this is the fabrication cost, and this is the fixed cost. So that you can compare what is the total cost for fabrication and machining, because if we are fabricating through VAM, we need machining. Machining is an important part in VAM. So without machining, we can't sell the product. Like we can't have a near net shape product so that we can deliver to the market. We need some type of subtractive manufacturing. To traditional subtractive machining can be done. So that is the this thing that we have to improve. So cost per part as function to the annual production for VAM processing chain and traditional subtractive approach. So cost per part you can see here. This is the cost per part and this is the annual production. If we are increasing the annual production, the cost per part will be reducing exponentially. You can see for 1500 parts and then 15,000 parts, and what we have achieved for 1,50,000 parts also. So that is the difference. This is the exponential reduction in the cost per part. So if we are increasing the parts, then we are achieving a lesser cost per part value. So for mass production, it is good. So machining and VAM cost is there. You can see total. So the last part is of this presentation is mass customization and flexibility. So mass customization, this is not done in the practical situation. So this is smart scheduling coordinates multiple AM systems. So multiple additive manufacturing system we can integrate and we can fabricate a component on demand spare parts, patient specific implants, shorter lead time, greater design freedom. So these things can be done. VAM inherently offers high flexibility due to its adaptable robotically robotically controlled process, enabling creation of complex customized large scale metal parts directly from the digital design. So this process excels at the customization, allowing for numerous unique designs without a significant cost increase, facilitating rapid prototyping, on-demand production of personalized custom components, and hybrid manufacturing by adding material to existing structures. Its flexibility also extends to the on-site repair of damaged parts and multi-material fabrication for functionally graded materials, supporting diverse industry application in aerospace, automotive, and more. So these are the challenges. We are nearly the end of the presentation. Challenges: limited data sets for training, data imbalance, few defect sample, high computational cost of deep learning models, transferability of transferability of models across materials and geometries. Future directions are multi-sensors data fusion for better accuracy. So multiple sensor we can use, like for acoustic and optical and thermal sensors we can integrate, and we can put all the sensors in one system. Explainable AI for decision transparency, integration with cloud computing, closed loop control for self correction. So these are the application of AM process: aerospace, automotive, defense, medical, energy. In every sector of the industry, we need additive manufacturing for there. Like, it is very important term in now industries. So what are the conclusion? Smart manufacturing turns AM into a predictable, scalable, and industrial viable process by combining data, connectivity, automation, and intelligence. This is particularly important in VAM CMT, where process stability and quality consistency are critical for large-scale metal structures. Smart manufacturing makes AM predictable, scalable, and efficient, improves process quality, flexibility, and sustainability. Key enablers for industry adoption for AM technologies. VAM is promising for large scale AM, but defect remains critical. ML, machine learning based defect detection, are also there. Strong potential for smart manufacturing. Future fully autonomous self correction VAM systems are can be made. So these are the reference, and thank you.
Participant may ask their query in the chat box.
One question is there, I think: how do you foresee the future of smart components in manufacturing? Is this question for me?
Yes, sir. Yes, sir.
So actually, for future, smart manufacturing is very important. Like, we have to integrate sensors, because without sensor integration or without collection of data, we can't actually see what kind of defects, and categorizes what category of defects can be inbuilt during the fabrication. So by integrating sensors and the collection of data, and analyzing the data sets, and improving that with the ML models, and by simulating these models, then only we can justify, or we can make exact prediction that these process parameters or these things or these input variables will cause a best output or not. So without these integration, it is very difficult. Like with traditionally we have to do like many experiments, and then we have to cut the sections, we have to give for the testings, all the testings we have to do, and then we have to analyze the output after fabrication, after this destructive testings, all the destructive testings we have to do, then only we can justify the output. So that is all the material wastage that we are doing. But in future we will be doing the smart manufacturing, because to save the materials, save the cost by economical these things and sustainability part, we have to do smart manufacturing. So this is the future of industry and industry 5.0, that is integrating with the smart manufacturing and additive manufacturing. So any more questions are there? Hello?
Sir, there are no further questions. So thank you, sir. Thanks a lot for once again for joining
Okay,
us.
thank you, thank you.